This handout is one of the most important handouts, okay? Every electric circuit is actually a combinational circuit. It can't be a series alone. It can't be a parallel alone. It has to be a combinational circuit, okay? For safety, for regular operation, for anything, it has to be a combinational circuit. So it's one of the most important topics. It's also it will be the end of DC circuits and the beginning of AC circuits. Right here on the main slide, I got two combinational circuits. All right, we already covered the series, so you are familiar with this side of the circuit, the power supply switch and the series resistors. On the right side of the circuit, you should be also familiar with the parallel circuit. These three are in parallel, okay? Down right here, you should be familiar with the left side of the circuit, which is a series with a variable resistor or a potentiometer, which we called it actually pod, but that's just an abbreviation or a common name. It's just a variable resistor, pod 1, and we got pod 2. This is the right side of the circuit, is a parallel circuit. Okay, so this is a parallel circuit. It means all the resistors are in parallel. Okay. Here on the left side, all the resistors are in series connection. Also, I want you to keep in mind a couple of new terms for you. Those will be docking or loading, set points, and proportional. All right, so yeah, these are new terms: docking or loading, set points, and proportional. Okay. And also, I want you to notice that I got all these test points, but B and C test points, we covered those in series circuit. B and C test points in the green color, we covered them in the parallel circuits. What I want you to focus on is high, J, low. Okay, the high, J, and low. Once you know those test points, you can figure out the rest. Okay, but those are very important: high, J, and low. Very important for docking or loading, set points, and proportional. High on the bottom circuit, we got high, J, and low. So these are very important test points. Okay. All right. So all right, let's look at it in depth now. So here I have a combinational circuit. Again, left side is my series circuit board or series circuit. And then the right side is my parallel circuit. Excuse me. The operation for this combinational circuit, if I want to know how it operates, I have to figure out some values. All right. In order for you to know how something works, you have to know, what is it for? Like it measures what, it takes what, it outputs what. Okay. Because if this is 12 volt and this is 12 volt and this is 12 volt, you're not going to know it does what. All right. So again, the first thing we need to know is we have to determine and figure out the high, J, and low test points, which we call them potential points. Okay. So in order for me to understand how this one operates, the whole circuit, and why it exists, all right, I have to know my high, J, and low. And I want you to know that J is just a junction. It's a splitter junction. It splits the series circuit from the parallel circuit. It's just a point where the end of the series ends right here, and the start of the parallel starts from here. Okay, so it's a splitter junction between the series and the parallel. All right. On the left side of J, I have a series of resistors. On the right side of J, I have a parallel resistors. we will name the series resistors. Anything connected in series on the left side, we will name it as a throughput. Anything connected to the right side of J, we will name it as a bandwidth. Okay, a bandwidth. All right. I can add more resistors in parallel. What happened to my bandwidth? Increase.
Hey, Omar.
Yeah.
You said we're name it a what?
Bandwidth.
Bandwidth. Okay, I got you.
The throughput, we'll talk about in details, but the throughput is what makes it is the series resistors. And the bandwidth, what makes the bandwidth is the parallel resistors. So understand this, please. The more you add resistors in parallel, all right, your bandwidth increase. So yeah, the more resistors you add, the more paths or lanes you have. Okay, so the higher the bandwidth is. Bandwidth is related to the current, directly related to the current. So the higher the bandwidth, the more current is being drawn from the throughput. Okay, the more current will be drawn from the throughput. Okay. If I took those two resistors out, the B and C resistors out, those in parallel, if I took them out, throw them away, my bandwidth decrease. Bandwidth decrease, that means there is the current going through the throughput will also decrease. Okay. Now the second point, it says at J, you'll have those series resistors on the left side. On the right side, you have those parallel resistors. All right, so it's like you got two circuits, series circuit and the parallel circuit. All right. The combinational circuit has, circuit laws. Okay. Before we talk about the circuit laws, those are easy. Okay, 3 laws. We already covered those. Look, the whole book, I would say like 90% of the book only have 8 equations. And not only that, it's actually 4 fundamental equations. Okay, and the other 4 are just derived from the first 4. So, I want you to, if you miss something, go back to the series handout, look at the 4 equations. If you miss something on the parallel, go back to the parallel handout and look at the 4 equations. So 4 equations and 4 equations, and that's it. Okay. All right. The combinational circuit, it's all about, so this whole circuit, it's all about finding the resistance, the total resistance at J, finding the maximum voltage at J, finding the maximum current at J. Once I close the switch, I'll try to find the total resistance at J, the maximum voltage at J, and the maximum current at J. That's it. So for that reason, we have three equations. The first equation is the total resistance at J. So the total resistance at J, on the left side, I have a series. It's the total resistance in series, total resistance of series resistors. On the right side, I have, excuse me, I got the total resistance of the parallel resistors. You add these together, you'll end up with RT, the total resistance in the whole circuit. Okay. So again, the total resistance at J on the left side is the total of the series. On the right side is the total of the parallel. Here I put RTP inverted. In other words, RTP prime is the sum of the parallel resistors, the reciprocal of each parallel resistor, like 1 over R1 plus 1 over R2 plus 1 over R3. 1 over RT prime, R total parallel prime, is RTP. All right, so again, RTP prime is equal to so yeah, I want RTP, so I'll swap these two. It will be 1 over RTP prime. Okay, this is very common equation. Again, this will give me the total resistance. So at J, again, you have a total resistance of series, you have a total resistance of parallel on the other side. All right, now this is for the total resistance. The second one is the maximum voltage at J. And the easiest law we can use, we already used it in the series circuit. So the easiest law we can use is Kirchhoff's voltage law. Kirchhoff's voltage law. Okay. Kirchhoff's voltage law. So I want to, let's say, know the voltage drop across the throughput or the series. Throughput or the series are the same thing, right? So if I want to know the voltage drop across those, it will be the sum of those, the RTS, the total series resistance, divided by the total resistance as a percentage times the total voltage. All right. So what happened to the voltage right here? We add them. Those two voltages are in series, so you just add them. All right, so my VT is 24 volt, which I think on the next slide, which also shows at the bottom circuit right here. Okay, so VT is 24 volt. So again, I want to know the voltage drop across the throughput. It will be the total series resistance divided by the total resistance, the overall resistance, times the total voltage. That will give me the total series voltage. It will give me the voltage from here to right here. This is my VTS. The voltage drop across the parallel resistors is VTP, the total voltage of the parallel, all right, is equal to the total parallel resistance divided by the total resistance times the total voltage. Okay. Now the third one is the current at J. So look, this is the current, the arrow, the blue arrow. This current is the same current as here. So if the current, let's say, for example, is 20, if the current, let's say, is 20 milliamp, it will go through the parallel, it will be combined right here, and will come out from here to back to the source. So this one will be also 20 milliamp. Back to the source must produce the same current, 20 milliamp. You see that right here, 20 milliamp. So the current going through the series resistors, the current going through the series resistors is the same as the current going through the parallel resistors. All right, the current going through the total series resistors is the same as the current going through the total parallel resistors. So what is the current going through the parallel resistors? It's V divided the voltage divided by the total parallel resistance. Once I calculate it, and assume it's 20 milliamp, for example, then again, the 20 milliamp will be everywhere. 20, 20, 20, 20. Okay. All right. So let's look at it again one more time right here. Let me erase those. Okay. All right. So find the equivalent, the total equivalent resistance at J. Okay. On the left side of J, I have, give me guys the values of these resistors. What are they? This one is how much?
200. I mean 100.
100. That one.
220.
And the third one.
441.
You got orange, brown, black.
Oh, I thought that was yellow.
So what do you guys have? So what's the value if it's orange, brown, black?
331.
300, okay. So is it 300 exactly or is it 330 ohms?
No.
Is it 331 ohms?
Yeah.
Okay. Is it like 331 and then what? That's it? 331 ohms?
Yeah.
Okay, cool. So yeah, okay. So these are resistors connected in series. If I want to find the total series resistance, I need to do what with these resistors? Add them or subtract them? Directly add them, right? So when we add them, we end up with what? What is the total series? Like what is RTS?
51.
551?
600.
600, yes, correct, sorry. I don't mind if you put it 0, 600 and let's put it 0, 650. Just want to make sure like you know how to get the value. Okay, so that's the total resistance on the left side of J. Okay, on the left side of J, this is what J will see. We'll see 650. I'm sorry, 650 ohm. All right, on the right side of J, we will see what? I got these resistors are in parallel. What's the value of the first one? What is the value of this resistor, the very first one?
650.
650. Nice. What's the value of the second one? Still, we got 6, 5. And how many zeros?
2.
Yes, 2 zeros. And what's the value of the third one? We got still 6, 5. And how many zeros? Is it 4 zeros or 3 zeros? Look, I'm gonna keep adding zeros until you tell me to stop, okay? All right. So we got 3 zeros, 65,000. Oh. All right. So what is the total resistance right here? The parallel total resistance. RTP, the parallel total resistance. I need to do what with these resistors? Do I need to add them or subtract them? I need to what? Add them. Can I add them directly or add their reciprocals? I have to add their reciprocals. This one right here, the series is directly you add them 100 plus 200 plus 331. That one, no, you got to add the reciprocals. So it's 1 over 650 plus 1 over 6,500 plus 1 over 65,000. Okay. Once you add them, once you add their reciprocals, invert the answer and you get the RTP. So go ahead, guys, calculate it. Tell me, I'm going to give you guys 2 minutes. Tell me what would be the answer here. All right, the first one on the list, Mr. iPhone, what's the total parallel resistance?
5, 8. Oh, my phone 3.
Oh, that you, James, also?
No.
Yeah, you gave me so many answers. Thank you. What is the total parallel resistance? Uh, 5, 85. I'm gonna neglect that fraction. Well, yeah, I'll put it 585. Okay. Let me check, because this is 5, 8. Yes, 585. Okay. So this one 585. I'm gonna put it right here as 585. Okay. So I can replace the series resistors with one big resistor, have a value of 650. I can replace those parallel resistance or resistors with one smaller resistor that has a value of 585. Okay. If I want to calculate the total resistance in the whole circuit, I'll just add these two together. I'll add them together directly. 650 plus 585. Okay, 650 plus 585. the answer will be how much?
They give you 1235.
1235, correct. 1, 2, 3, and 5. Thank you. Okay, so it's first one is very easy, right? All right, second one, Kirchhoff's voltage law. Kirchhoff's voltage law. I want to know the voltage basically across the parallel resistance. To know the voltage across the parallel resistance, I'll take the parallel resistance, the total parallel resistance, divided by the overall resistance, and multiply it by VT, the total voltage, which is 24 volts. So again, I want to know this voltage. If you guys can see the screen, I want to know this voltage. This voltage will equal to this parallel resistance, RTP, divided by the total resistance, the overall resistance, RT. And then you multiply the results by the overall voltage, the 24 volt. So it will give me an answer in voltage, because ohms divided by ohms cancel out. It will give me a unit, a number that has a unit in voltage, right? What is it? How much is it? So divide 585 585 by 1235. Times 24 volts. This will equal to, I think, somebody wrote the answer. Yes, correct, 11.4 volt. Thank you. 11.4 volt. Now look carefully here. This point is 11.4 volt. This is ohm. I'll put it right here. Ohm. Okay, so 11.4 volt. What is the voltage at the low point? What is the voltage here? This is the lowest potential, right? So it's 0 volt, right? This line right here is a 0 volt line. When you measure the voltage, it measures across these 2 points. It subtracts the voltage here minus that one. 11.4 minus 0 volt is 11.4. That's the voltage across your parallel. Okay. All right, let's do the same calculation now. Excuse me. Let's do the same calculation to figure out the voltage across the series resistor. Okay, I want the voltage across the series resistor from here to right here. I want this voltage. To know this voltage, think I got a quick answer. Nice. Yes, correct. So if I want to calculate this voltage, it will be the total series resistance divided by the overall resistance times 24 volts. All right, the total series resistance is 650. Let me erase the blue line. Divided by the overall, which is 1235, 1235 ohm, times 24 volt, it will give me 12.6. But anyway, this is 12.6 volts. 12.6 volt. Okay, let's understand exactly where it came from. Look, the high point is attached to the voltage directly, right? So we know the voltage at the high point is 24 volt. You guys see that? The voltage at the high point is 24 volt. And the voltage of this line is 11.4 volt. The voltage of this line is 11.4 volt. So it doesn't matter if I draw this voltage here or all the way to J. It's the same thing, okay? So I'll put it just on J. So when I measure the voltage across the series, the throughput, when I measure the voltage across the throughput, it will be 24 minus the voltage right here, which is 11.4. And this will give me 12.6 volt, okay? You can either use this calculation, Kirchhoff's voltage law, very, very common. And kind of you have to use those equations a lot, Kirchhoff's voltage law, because you're not going to be measuring things, you'll be calculating things. So again, when you measure the voltage, you have the two leads. The red one comes here, the black one goes to J, and the voltmeter will measure the difference, which is 12.6. Okay, so the voltage, the throughput voltage is 12.6. Your parallel, the bandwidth voltage is 11.4. Okay, let's continue, but this time let me change the color to red. All right, now I want to know the current. Okay, I want to know how much is the current. This arrow, how much is it? The same as this arrow, which is the same as that arrow. Goes back to the source, the voltage source. So how much is this arrow? Well, there's only one equation here. It's the parallel voltage divided by this resistor. That's it. You divide the voltage by this resistor, you get the current. The voltage of the parallel is 11.4. You divide it by the parallel resistance, which is 585. Okay, 585. You'll get what? Perfect, nice. 19.5 milliamp. So when you divide these two, you'll get a fraction number. You got to convert it to milliamp. So you can get like, you know, a whole number, a decimal number. 19.5, 19.5. Okay, milliamp. So what is the series current? This is the parallel current. This is this current right here, 19.5 milliamp. This one is 19.5 milliamp. So what about this one? Is also what? 19.5 milliamp. The one that goes to the series, 19.5. And then it goes to the parallel, 19.5. So this is 19.5. Milliamp. This one is 19.5 milliamp. Everything here is 19.5 milliamp. Okay, clear? All right, that's it. That's you just solved a complicated circuit called combinational circuit. It's the heart of all electric circuits. Now, when you combine this with the logic circuits, you'll end up with a powerful device. Okay. So, yeah, 19.5, 19.5. Let me just put it right here, 19.5. All right, you go to any place now. You can be hired as engineer because you already know all the calculations. Measurements, your parallel lab will have a lot of measurements, so you'll learn how to measure voltage, current, and resistance. Measurements are easy, but the concept, how to predict what would be the voltage, what would be the current, is the most important thing. So save. All right, any questions? Anyone have any questions? Does anyone have any question, guys? Okay. Second slide is just more, a little more terminology, okay? So go ahead, take 2 minutes, read it, and then I'll go through it, okay? All right, so we have not done the operation yet, okay? But I want you to understand that the left side of J is called a throughput. That's the left side of J. And the right side of J is called the bandwidth. Okay. Throughput main job, so those resistors, their main job is to give J a voltage and a current. Is to give J a voltage and a current. And then I don't care about anything else. Anything, you can attach anything here if you want to. A motor, a capacitor, anything you want, any kind of load, a TV, whatever you want. Okay. But throughput is very important. It sets up your docking voltage and your docking current. Okay. It sets up your docking voltage and your docking current. Now, on the right side of J is called bandwidth. The bandwidth ranges from 0 to maximum docking current. To maximum docking current. Okay. Now, here's the deal. When one circuit board is docked or attached, when one circuit board, let's say, is attached, you're not going to reach the maximum current. You'll reach a certain current, all right? Not yet the maximum, not 1 amp yet. The more circuit boards are attached, the more we have circuit boards attached, you'll reach the 1 amp. Your bandwidth will increase. The bandwidth will keep increasing until you reach the maximum current. Okay, the maximum current of J. okay? Not the maximum current of the source, the maximum current of J. All right. So throughput is very important. It's called a set point, has another name, set point, but you will hear this a lot in level 2. Level 1, you just need to know that this is called a throughput. It sets the docking voltage. So if I want to attach circuit board right here, the docking voltage is 12 volt, for example, because J is 12 volts. So anything on this line attached to this line is 12 volt. All right, this type of throughput is fixed. It always provide me with a J voltage. All right, we already calculated, and it was 11 exactly. The voltage was let me choose green color, 11.4 volt. But if I want to provide like let's say 18 volt here, then I need to physically replace these resistors, maybe one resistor or two. Okay, if I want to have different voltages, then I have to physically replace those. Because these resistors on the throughput are fixed type, then it's called a fixed throughput. Okay. However, variable type is also common, but it's more expensive. All right, it's more expensive. Bandwidth, also called the limit. But again, these two terms, you'll hear them in level 2, okay? So you don't have to worry about them on the quiz. This is level 2. What you need to know is that bandwidth is related to the docking capacity and transmission capacity. All right, we'll go a little in details. Bandwidth range from 0 to the maximum docking current is fixed. So let's say 0 to, let's say 40 milliamp. Okay, that is fixed. But variable can be also set. You can buy one with a variable bandwidth. Again, the price will be also higher. Okay. Either you build your own or you buy it, but yeah, the price will be much higher. So for example, if I want to buy fixed throughput, fixed range bandwidth, let's say the price for these two, let's say $20. If I want to buy variable throughput and variable range bandwidth, the price will be $200, from $20 to $200. All right. Now we got to focus on something called the maximum voltage at J. How much is it? Maximum docking current, how much is it? I know we did calculation 11.4 and a current of, what was the current? 19.5, right? 19.5 milliamp. These two are not the maximum docking voltage and maximum docking current. They are not the maximum voltage, docking voltage, and the maximum docking current. They are not. But I have to know what are they? What's the maximum voltage and what's the maximum docking current? And that will be the next slide. Anyone have any questions so far? Any questions? Excuse me. So I need the maximum docking voltage and the maximum docking current. How I can figure out the maximum docking voltage and the maximum docking current. So this is my series resistor. This is 650 ohm, 650 ohm. Yeah, that one is 650 ohm. Okay. Let's look at let me go back here. You see those three resistors? Parallel resistors. It starts with 650 ohm, right? It starts with 650 ohm, and then here I have 6,500 ohm, and then here I have 65,000 ohm. Okay. So now look, this is the 650 ohm. And let me write it down, 650 ohm. Here, I replace the 6,500 and the 65,000 with a higher load. I want to explain to you what will happen if I attach a very big load. What will happen if I attach a very big load? So this one is blue, green, and yellow. Let me write the value on the top. This one is 6.5 with 5 zeros. Again, those are very big values, okay? It could be even higher. It could be 100 million, whatever. Huge load. All right. But for now, this is what I have. So tell me, what is the equivalent total resistance in parallel for those three? If I want to calculate RTP, please go ahead, calculate RTP. Tell me RTP will equal to what? This is the docking points where I attach loads. So it's equal to what?
649.
649, which is equal to this one right here, 650. 649, 649.3. Okay, nice. Yes, so it's equal actually to that one, the 650, right? The higher the load is, even if you apply a higher load, okay, it will get you very close, so close to this value. All right, so when I attach very, very big load, I'll get 650 ohm, a total of parallel resistance that is equal to 650 ohm. All right, that is actually equal to the first resistor right here, the smallest resistor I have here, 650 ohm. So this 650 ohm resistor is very important, and it's called the docking resistor. Okay, all the other resistors on the attachment points, all the other resistors are called load resistors. So my RTP, the total parallel resistance, it consists of a docking resistor and load resistors. Okay. So if the load is huge, then your RTP will equal to the docking resistor, 650 ohm. So now let me erase those values. So now I got 650 ohm on the throughput. I got 650 ohm on the parallel. What would be the voltage at J? If I attached a huge load, what would be the voltage at J? I got 24 volt. The 24 volt will split equally among these two resistors. So this one will be how much? 12 volt. And that's my maximum docking voltage. So let's go right here. Maximum docking voltage when RTP equal the largest value. RTP will equal the largest value, which is equal to the docking resistor, the 650 ohm. Okay, when RTP is the largest value, I'll get the maximum voltage, 12 volt. Okay, and it's maximum voltage, maximum docking voltage. So now you can predict if I attach a huge load to my circuit board, to my combination circuit board, I'm going to expect J to be 12 volt max, maximum 12 volt. All right. So this is number one, is right here, number one. Let's look at number two. Number two. Again, this one is 650 ohm. It's fixed throughput, 650 ohm. This is my docking resistor. So this is my docking resistor, 650 ohm. What will happen if the load is so small? If the load, not in size, but I'm saying like if the load has a very small resistance, in that, for example, you can replace your load with a wire. So imagine there's a wire attached to here. And this is now my load. It's just a wire, and the resistance of that wire is 1 ohm. Go ahead, please calculate the RTP. Please calculate the RTP.
I got 0.998.
So in this case, this is 1 ohm, or smaller than 1 ohm. But anyway, in this case, my total value is assuming 1 ohm, or approximate to 1 ohm. If you think about it, I mean, you just short out the docking resistor. You're bypassing the docking resistor. So now this is 1 ohm, okay? All right, so now I want to know how much be the current, the maximum current. So the maximum current will be what? The 24 volt divided by 651, which is about 40 milliamps. I need red color, that's red color, yes, 40. Right, 40 milliamps, yeah. So if I want to know the maximum docking current, the 40 milliamps, the maximum docking current, I need to say or ask myself what happens if I attach a very small resistance, a load that has very small resistance. Then my circuit will jump to a maximum docking current that is 40 milliamps. All right, so now you got a maximum voltage 12 volt. You got a maximum current of 40 milliamps. So your maximum docking current is 40 milliamps. Down right here. You know, if I attach big loads, definitely the voltage they're gonna take is 12 volt maximum, and the bandwidth or a current range from 0 to 40 milliamps. Okay. All right, so now at J, I'll have the following. I have V max docking that is equal to 12 volts. I have I max or current max docking equal to 40 milliamps. Okay. You know your max limit is 40 milliamps. So your current range will be from a minimum value to 40 milliamps. Your maximum voltage is 12 volt. Your maximum attachment voltage is 12 volt. So you know the voltage range will be from a minimum value, which is I don't know, 11 something to 12 volt. Okay, we'll talk about the range on next time. Please stay tuned on D2L. Again, Zoom always records the attendance, guys. Unfortunate if you've been an absent, that's unfortunate for you and for us. All right, anyone have any questions? Okay. All right, if nobody have any questions, good luck on your next class. Stay tuned on D2L, and I'll see you guys next time. All of you have a good day.
You too, bye.
Bye.
Hey, Omar, I got a question.
Yes.
For this video, this is Jay. Am I able to, I know you're recording, am I able to rewatch it? Is it on D2L? All right, I got you.
So yeah, I will see what I can do.
Cool beans.
All right.